good evening, everyone, and welcome to this fifth talk of the Exoplanet course. So today we have with us Dr. Manoj Puravankara, and I would now request Dr. Ravi to introduce our speaker for the day.
All right. So thank you everyone for attending this session. We have a distinct pleasure of having Dr. Manoj Puravankara from Tata Institute of Fundamental Research. Dr. Puravankara is really an expert in star planet formation and also in protostars and protoplanetary disks. And he kindly agreed to talk to us about exoplanet characterization and demographics. This is one of the most important topics in the exoplanets because we have been discovering so many of them. So Manoj, whenever you're ready, please.
Hear me now?
Yes.
Yeah. Thanks, Ravi. Thanks, Prachi, for organizing this. Thanks for inviting me. As Ravi said, I want to talk about exoplanet characterization today. Primarily, I'll be talking about exoplanet demographics. It's not going to be very exhaustive and comprehensive. I mean, I will lean towards some of the things that I've been doing. So there may be stress on some of the topics that I and my group have been working on. But before I begin, let me just want to say that, feel free to ask questions in between the talk as well. You don't have to really wait towards the end. So we can sort of make it more interactive. Let's begin. And this exoplanet demographic. So as you know, so we now know, well, until about 1995, this was probably the only, planetary system that we knew of. This is artist's conception of solar system. But now we know more than 5,000 such systems for sure. And we believe most stars in our galaxies probably host a planetary system, perhaps more than one. And here the video that you see is one such system that we have discovered. The central star is blocked, starlight is blocked, and you can see 4 planets actually moving around. This is a time series, so images taken at different points in time, and then you just run them together, and you can actually see orbital motion. This is the simple harmonic motion in nature. So with that, let us begin. So I want to talk about demographics, but before that, I just wanted to provide the context for it. So it has been 30 years, since the first planet around an astrophysical object outside of our solar system was discovered. As I was telling you, until about that was in 1992. Until about 1992, our solar system was the only planetary system that we knew of. And that is what I've shown here. So you see the 8 planets in our solar system, and then these 2 purple ones. These were discovered not around a sun-like main sequence star, but around a dead star called pulsar. And this was the first exoplanets that were discovered. But it was in 1995. It was in 1995 that the first planet around a sun-like normal main sequence star, which burns, hydrogen, was discovered. So that's, as you all know, it's 51 Pegasi, half a Jupiter mass star, so planet orbiting very close to the central star. And the discovery was, of course, made by Michel Mayor and Didier Queloz, for which they won the Nobel Prize in physics in 2019. And so since then, in the last 30 years or so, the situation has dramatically changed. So I've chosen to represent it in a plane of, on the y-axis, it's the planet mass in the units of Earth mass. On the x-axis, it's orbital distance in the unit of Earth-Sun distance. And you see the current situation here. So the solar system planets are here. You see plenty of them. Different colors here represent different detection method. You probably heard Joe talk about it yesterday with various detection methods. So it's dominated by transit method. And one of the things that you notice is that most of the systems are very close to the central source, the architecture. They are quite compact. You can see the solar system planets, and the orbital distance to them are quite large. And most of the ones that we have discovered are quite compact systems. And this is largely a selection effect because of our detection techniques and the current technology and sensitivity. But this need not represent the true distribution out there in the universe. But the very existence of such systems itself is surprising. You can't deny the fact that they are there, these compact systems. But you also then detect very extended systems, Jupiter or super Jupiter, so planets which are much more massive than Jupiter's. Jupiter is here, and this is the planet mass axis. And planets which are much more massive than Jupiter's, and at 100 times the sun, beyond the solar system. Our solar system probably here is Neptune's orbit, right? And maybe there is some Kuiper belt objects beyond that, but some of these things that we have, massive planets that we have discovered are far out. So this is just to give you an idea of what we are, the sample that we are dealing with. This is slightly, a few months old data. Now the total number detected is, I think, 5,200 or something. This is another way of representing the same thing. The cumulative distribution of detection. As you can see, this probably has already been talked about. The radial velocity technique dominated the detection statistics until about 2013 or so. And then this green thing, the transit, starts speaking. And that's largely because of the Kepler satellite, which was a space mission by NASA, which just stared at a piece of sky for 4 years. And these two detection methods, transit and radial velocity, account for 99% of the planets that we know now. Out of this, over 5,000 planets that we know, 800 are in multi-planet systems. And I think Saurav Chatterjee, my colleague, will probably talk about them and their architecture tomorrow. I'll not talk very much about them. And there are about between Kepler TESS and K2, there are about a few thousand candidates which are yet to be confirmed. So what really the impetus that is provided for the demographic studies, really the statistics, the numbers that we have detected now. We have over 5,000 planets, and it's possible to do some statistically significant studies about their properties and all that. Remember, for a long time, for centuries, we had only one data point, right? Our solar system. Now at least we have 5,000 more. So there are various things that we can look for, So how does the planet properties depend on the stellar host star properties, or how, and what's the distribution of the planet radius, planet mass at different, around different stars, etc., etc. But what we immediately realized was that there is a large diversity in the planetary systems that we have been discovering in the last 30 years. This is again an artist's conception. The closest exoplanetary system to us, it's Proxima Centauri. The 3 planets, one is disputed, but the 2 for sure, which are quite close to it, an Earth-like or even smaller than in mass, the Earth planet, orbiting very close to the star. And you also have Kepler 90. See, until about 2017, solar system was the only planet with 8 planets, only planetary system with 8 planets. Not anymore. Kepler 90 has 8 planets, and the planets are stacked together roughly with the terrestrial or the rocky planets inside and the giant planets towards outside. This is not at the scale, but this entire system is very compact. I think the Kepler 90H, the outermost planet, is at the Earth sun distance. Really, so it's compact, but yeah, so we are not unique anymore. There are planetary systems out there with 8 planets, and even there are all other kinds of diversity. So these are mostly, we were discovering compact systems, and one such system is TRAPPIST-1, which have 7 planets, but that's what is shown here. But this entire system could be tucked into within the orbit of Mercury. It's very compact, extremely compact, and this has been the one of the features that most of the systems that we have discovered have been very compact. But then we also have, as I was telling you from the earlier figure, that quite extended systems, and HR 8799, the time series that I showed earlier, it has 5 gas giants like Jupiter, like planets, at the distances from 15 AU. 1 AU is Earth Sun distance, so 15 times the Earth Sun distance of 75, much beyond the extent of solar system. Right? And this is a relatively young system too. So it's quite diverse in terms of planet properties, system architecture, etc. And then that is what we will see in the demographic study. And I'll highlight some of the results that we have learned these studies. But before we go there, so what are the big questions here in exosolar or exosolar planetary studies, exoplanet planetology or exoplanet studies? I think the overriding motivation or aim, in my opinion, is placing the solar system in context. To understand how planetary system like our solar system form as a part of the star formation process, and understanding these processes that drive planet formation. That's one. And then of course, the asking the question, is solar system a cosmic rarity, or so to say, the galactic commonplace? Our solar system quite common in our galaxy, or is it unique? Of course, there is the question of life on other world, the formation of Earth-like planets, and how do they come to sustain life. And with this overriding objectives, the frontier areas in exoplanetary science are, if one were to reduce, so there are, I don't want to claim that these 4 are the ones, the primary ones, but just to highlight this. Exoplanet demographics and atmospheric characterization, star-planet interaction, habitability, and search for habitable planets. And they kind of inform on some of these issues. Don't take this very seriously. This is just, delineating, kind of trying to put it all together. So in this talk today, I will restrict myself to talking about exoplanet demographics and if time permits, towards the end, star-planet interactions, and on which I and my group have worked a little bit. All right. So as I was saying, the exoplanet demographics is primarily driven by these numbers. Now we have the statistics to carry out meaningful studies, about the relation between planet properties. The observed, see what we can really observe about exoplanetary systems. There are many things, but the primary things are the other planetary properties, such as radius, mass, and orbital period. See, for example, both radial velocity and the transit technique, both will give us the orbital period. And the transit observation will give you planet radius. You can measure the planet radius, and the radial velocity technique will give you the mass, planet mass, uncertain to the degree of the orbital inclination. And there are ways of deriving eccentricity and all those. We don't go into those details. But so the question, so with these properties, one can really see how planetary systems are, how similar they are, how different they are, how these properties distributed, etc. And then that is what I'm going to show you today. So what I'm going to tell you today is what have we learned so far. And this is not again an exhaustive list, and I'm focusing or stressing more on some of the things that we are interested in, and I and my group, and highlighting some of the kind of placing the result in a larger context. Some of the top level answers. So I start by summarizing the 3 major things that we have learned, and I will go into each of them one by one. The first is a thing that we have learned in the last 30 years, having discovered several thousands planetary systems, is that planetary systems are ubiquitous in our galaxy, of course, and by extension in our universe, perhaps. And in fact, one of the greatest contribution of Kepler satellite has been this finding that there are more planets in our galaxy than stars. What it really means is that for every star, if you are using Kepler data, if you calculate what's called the occurrence rate, I'll explain it in a bit. There are about more than one planet per star in our galaxy on average, from what we know. The second point that we have learned is that solar system is not an archetypal planetary system. It's the planetary system that we know for sure, that we have detected so far, do not look anything like solar system. And as I cautioned you in the beginning, there's a lot of selection effect here, and it's not very clear whether this is what we have discovered, what we see is the real distribution out there in the universe, or this is just a selection effect because of our selection technique, technology, sensitivity, and various other factors. But what we know for sure, the planetary system, they don't look like our solar system. And the third one, perhaps in my opinion, the most important realization that we have had from these studies is that planet properties are closely connected to the host star properties. It's almost as if planets know what kind of star it's being born around. So this gives us important clues, or deep insights into how the systems probably form in the first place. And this also leads to this big debate about whether planetary systems, mature planetary systems, preserve their memory of their birth or not. And there's this big debate raging in the literature right now. Now let us look at each of these separately. The first about the ubiquitousness, or how the fact that planetary systems are common. And how do we know about this? To learn about this, we see it's not enough to just look at a piece of sky and count the stars, number of stars with planets, and then divide it by the total number of stars that you looked at. That will not give you the real fraction of stars with planets, right? Because there are a lot of selection effects, so and observational biases and all that. So to avoid that, what we do is astronomers, astrophysicists calculate something called occurrence rate. It's simply the mean number of planets per star having properties such as radius or orbital period in a given range. You can do it whichever way you want. And it's just given by this equation, number of planets detected with the particular radius property, radius in a particular range, or orbital period, we can decide. And the number of stars surveyed. But see, for example, if we had surveyed all the stars in our galaxy with instruments which are infinitely sensitive, then all we need to do is just write down the number of planets detected here and the numerator, and then total number of stars surveyed, and that will give you the occurrence rate right away. But unfortunately, we cannot do that. So as I told you, Kepler just looked at the piece of sky, 10 degree by 10 degree for 4 years, and there were about 250,000 stars there. But you need to correct for various things. For example, the Kepler detected planets using what is known as transit method. So you need to correct this number, the observed number. So you would have observed certain number of planets, and you know how many stars you have surveyed, but you have to correct for geometric probability of transit. This is easy to understand, right? I mean, so your star, and if the planet is going around, if the orbital plane is perpendicular to you, the star planet, you know for sure that the planet will block light coming to it, and you will observe a transit. But what if it is face on? The planet can keep going around, and you will not observe a transit. So you have to correct for that, the geometric probability of transit. But that is not enough. Even if the geometry is favorably aligned, because of your detection sensitivity or emissions, you may not be able to detect those. You have to correct for that. You need to know what is your detective threshold or efficiency. And the third important point is this noise level of the star. This can often cause false detection. See, the transit is when the planet moves around in front of the stellar disk, and the flux dips a little bit. So this can sometimes can caused by star itself, stellar light flux itself is fluctuating. So we need to have a good understanding of that. So, and there are certain minor things which may not be that critical. But if you do all this, and you can calculate this occurrence rate, and then I'm going to give you a summary of what we find. So this is the occurrence rate per 100 stars. I have chosen to light it into 100 stars in a given radius range. So 1 to 2 Earth radius, we typically call them super Earths, and 2 to 4 Earth radius is many Neptunes. 4 to 8 Earth radius, Neptune-Uranus regime. So that's sub-Saturn, so Saturn's, and this is the Jupiter, the gas giant regime. So you can see that the one thing that you immediately see from here is that the gas giants are relatively rare, whereas smaller planets, super Earths and mini Neptunes, are quite ubiquitous. In fact, the mini Neptunes are the largest fraction, are the most common planets in the among the planetary systems, exoplanetary systems that we have discovered. So smaller planets are much more common than gas giants. That's one take-home message. So it's about super Earths are about 50% of the 50 out of 100 stars, so it's about 0.5 occurrence rate, and this is about 60, so this is the most common one. You probably know what we mean by, so the smaller planets are, we often call terrestrial planets, which in our solar system are Mercury, Venus, Earth, and Mars. And the Uranus and Neptune, we call them ice giants. I might use this terminology in the late talk, throughout the talk. And gas giants are Jupiters and Saturn, because they're predominantly hydrogen helium envelope. So again, these numbers I have listed here, the Earth, super Earths, and this numbers will slightly vary from other estimates depending on the radius bin that you use. So we have chosen, but then the take-home point here is, is there something on the chat? I should be watching this. Yes, Ravi is asking a question. I have to say this all this occurrence rate that I'm showing you, it's primarily based on Kepler data, and it's really complete only for an orbital period of 1 year, less than 1 year, roughly on that. Because whatever results I'm saying, and I would have said this later in the talk, it's strictly true only for planets with orbital period less than 1 year. So these are the occurrence rate again with numbers. So smaller rocky planets are much more abundant than gas giants. So since we are talking about demographics, we can also see if you measure the planet with both transit and radial velocity technique, Doppler shift method, you can measure both mass and radius of the planet. And also the orbital inclination, so the true mass as well. So, and if you plot such the planets, the radius and mass in this figure, and then you can compare them with some models, models of, so that is what I've shown here. So these lines, solid lines are, so for example, if you take this blue line, that's 100% iron, rocky planet 100% iron, and then orange is 50% iron. These are simple models, and I just wanted to show you that already if we can measure the mass and radius, already we are able to say something about the bulk composition of the planet. So you see Saturn and Jupiter are here, so it's these are kind of gas giants, and so this you can also talk about whether it's water content and atmosphere and all that. But what is really interesting is planets here. These are planets with much larger radius for its mass. So inflate sort of rare atmosphere, low density atmosphere. This is seen better in the density planet radius plot. So these are bulk densities. If you measure mass and radius, you can get the bulk densities. And this I've shown water density 1 here, and then the Earth's density about between 4 and 5. You again see this bunch of sources between so these are the most common planets, the sub-Neptunes or super Earths, which show this sort of densities. They have some atmosphere, and they're not entirely rocky. Yeah, so that's about. So these are the kind of things that you can do with demographics. So now we know of Yeah, there is a question here. Why are the models not extended to massive planets? Yeah, massive planets, they have slightly different. So mass radius relations are not exactly the same day. And they have slightly different, they need to do slightly different calculations for that. So you can get the hydrogen helium thing here, but that sort of will, that probably can extend because massive planets are mostly hydrogen helium. For example, Jupiter is 300 times the Earth's mass, and it's most of it is hydrogen helium. We believe that it has about 10-15 Earth mass of the core, rocky core inside, but it's mostly. But these things you can't really extend towards the giant planets, but these are really rocky planets. There is another question. I have a question regarding occurrence rate. How many stars have you surveyed till now, and how many exoplanets have been able to detect? I mean, occurrence rate of super Earths, which you have showed, it can change after some years if more exoplanets are detected. The occurrence rate is, as I was just saying, occurrence rate is sort of true if you restrict ourselves to orbital period less than 1 year. So Kepler, this occurrence is mostly from Kepler data, so it's sort of complete till 1 year. And if you apply those correction factors, the transit probability and then various other detections are shown and all that, you get a reasonable number. So up to 1 year, these results, orbital period of 1 year, these results hold. Now, the parameter space that we have not sampled yet, that's a different question altogether. And we believe, and we are now discovering more and more planets at longer orbital periods. So that's a different question. But within orbital period of 1 year, these results occurrence rates are more or less okay. There is another question. Okay, Jupiter-sized planets are easy to detect in transit method compared to Earth-sized planets. So we have a large number of sample of Jupiter-sized planets compared to Earth. Then how could we tell Earth-sized? Yeah, so as I was saying, see, we are not going by this observed numbers, no? So we are all this what you just said about the selection effect. Jupiters are easier to detect. All that goes into that correction factor that I was talking about. So you have an observed numbers, but then you try to correct it for various selection effects and biases. And that is how you get the occurrence rate. And that's the true rate, at least to the orbital period within 1 year. So the second thing that we have learned is that the solar system is not an archetypal planetary system. So there are various reasons why we say this, but let me just highlight a couple of them. So one of them is, as I was telling you, if you were to just do the, so even just the observed numbers, this is not corrected for occurrence rate, just the observed number. The most of the planets, exoplanets that we have discovered, fall into Earth and Neptune category. It's not, even though Jupiters are easier to detect, we don't detect as many Jupiters. So that even further brings down the true number. So the most of the ones detected are these. The planet, the most common planet, the detected, have radius and mass between that of Earth and Neptune. And then if you apply those correction factors, this number goes up, right? I mean, so there are 10 times more this super Earth, mini Neptune kind of planets than Jupiters, roughly, within an orbital period of 1 year. And as you know, our solar system does not have such a planet. The most common planet, at least from what we know so far, does not exist in the solar system. And if you also, if you were to plot the distribution of orbital period in days, and I've shown the orbital period of Mercury, which is 88 days here, orbital period of Earth, 365 days. You see, this is just the observed numbers. You see, the most of the observed planets have orbital periods of 8 to 10 days. So they're very much more compact systems. There are selection effects here, but even if you correct for all this within 1 year, planetary systems with orbital periods within 1 year, so these are the true numbers. So it's very different from our solar system. What we are discovering is very compact systems. So it's still an open question whether solar system is really a true representative system or not. I mean, one could argue that we are only complete up to orbital period of 1 year, and there might be systems out there which we are not detected, the parameter space that we are not explored, which could be very much like a solar system. But from what we know, solar system doesn't look like a representative. At least there are systems which look very, very different from solar system. So solar system may not be very representative. Which you can see here also in this plot of planet mass and orbital distance, which I had shown earlier. So here are the solar system planets in cyan color. So most of the planets that we have discovered are very compact sources. And then you also have this much more extended sources, the planet systems. All right. There is a question, how many of these planetary systems have host stars like Sun? Yeah, I'll come to that. So that there again, you have to correct, right? We are not sampling all the stars. Yeah, so I'll come to that. That's the next thing. I'll have more to say on that. The third thing the general thing that we learned is that the planet properties are closely connected to the host star properties. Now, what am I talking about? The observed planet properties, which are mainly radius, mass, and orbital period. And the host star properties are, typically observed properties are the spectral type or the effective temperature of the star, or the metallicity of the star. I'll explain what that is. And the age of the star. So these are all parameters to be derived. See, effective temperature is probably measurable. You can directly measure it, but the other quantities, metallicity and age, all have to be derived. It's not an observable. Nevertheless, so let's not see the planet properties as a function of host star spectral type. What does it tell us? So before that, before we see how it the patterns, let us first talk about what are these star types. You probably already know what spectral types are and and how it corresponds to the temperature. So the most massive stars, the O-type stars, spectral type O-type, they look bluish and they have extremely hot temperatures. Whereas the F and G, the Sun is a G-type star. It has a temperature between about 5,700 Kelvin, somewhere in this range. It's a yellow star. And then if you go to cooler stars, stars cooler than Sun, they appear red, orange, and they are K and M. So Kepler, in the Kepler field, I mean, the stuff I'm showing, the most of these stars that we have looked at so far are FGK type stars. F star, very few F stars, but mostly GKM, and sun-like stars and then cooler stars. Okay, so we'll be only talking about these stars with temperatures less than 8,000 Kelvin. And this is what occurrence rate tells us. M-type stars host many more planets than K-type and G-type stars. So take G-type as a sun-like star. So this is per 100 stars. So M-type stars actually, M-type stars have 2 planets per star. As opposed to, this is for all kinds of planets, as opposed to sun-like star, it's about 1.5 roughly, and F-type really is small, 0.7. Less than a planet per star. So cooler stars cooler than Sun have host more planets. However, if you now do the occurrence rate in terms of radius, one of the things that you find is that cooler stars, most of the planets around cooler stars are rocky, small planets, and they seem to avoid the gas giants. The colors that I've shown here for the histograms are: red is M-type, green is K-type, blue is G-type, and purple is F-type. So although cooler stars host more planets, most of them are smaller planets, and they don't seem to host many giant planets, Jupiter-like giant planets. They are mostly in around sun-like stars. So that's about the planet and T effect, the spectral type dependence. To summarize, cooler stars host more planets, and these planets around cooler stars are mostly rocky planets, smaller planets, and most of the gas giant planets are around sun-like stars, a little more massive sun-like stars. Now we move to so maybe maybe I can stop here and take some questions. If you want to ask questions, we can have a few now before we move on to the other property. Can they unmute and ask
Yes.
questions, Prachi?
Yes, participants, you can unmute yourselves. Harshita,
Yeah,
you
there
can
is a
go ahead.
hand by Harshita MP. Yeah, please go ahead, Harshita.
Yeah. Hi, Professor. I just had a question about off main sequence stars. Like, has there been any demographic studies about?
Yeah. So this study I'm showing here, I should correct that. This is only for main sequence stars. So we haven't
Okay.
looked at the post main sequence stars. So, but I can tell you that So as of now, we have detected planets around post. By post main sequence, I mean stars which have exhausted their hydrogen supply in their core and are
Mhm.
evolved off the main sequence. I hope you have done stellar evolution. So there are about
Yeah.
200 post main sequence stars around which planets have been discovered, but we have not been able to apply these corrections for them because they are not very representative
Mhm.
sample, and they are mostly predominantly. I don't think you can't really say. So to answer your question, yes, plants have been discovered around post-main sequence stars, red giants, etc.
Yeah. But do they have any unique features or like
See, that
maybe
sample is too small, and as I was telling you, we
uh,
cannot really apply this correction, and we cannot go by the observed numbers. No, So the observed sample, what you can say, they are mostly giants, gas giant planets like Jupiter's, and slightly away from it's about 1 to 2 AU distance, slightly more distant from the source. But it's there are a lot of selection effects there.
uh, uh, thank you, Professor.
Any other questions? There is one question on chat. What leads the cooler star to have more small planets? Yeah, so that's a question that is not entirely answered, but we have people have been talking about. Maybe towards the end there are a bunch of other things also which I want to show. They are all connected. Some of the trends that we see, not just in spectral type, but also what I'm going to introduce now, the stellar metallicity. So they're all probably connected, and we'll come to that. So the quick answer to your question is it's telling us something about the formation. Are there any more questions? Otherwise, I'll proceed.
Not in the chat box.
Okay. Then let's move on to the planet properties and the next host star property, which is the metallicity. I hope you have done some stellar evolution course or something. It's metallicity. See, stars are composed of elements, right? I mean, and the most abundant element in the universe is hydrogen. The second most abundant element is helium, and the third most abundant element is oxygen, and so on.
Sorry to interrupt you, Professor.
Yeah.
I had a question that is it possible to host M type of star to host a heavy planet, just like having same mass as the star?
As a star.
Yes, because I think in your previous graph you shown that massive stars, massive planet doesn't found inside in other stars less than I think in K type star.
No. So your question is, can there be another star around an M type star?
No, and that like I'm asking for massive planet, just like Jupiter.
Statistically, they seem to be fewer in case. That's all we can say. And this doesn't mean that there are no massive planets around an M-type stars. And remember, please bear in mind that all that I'm saying, all the results I'm showing is strictly true only for orbital period less than 1 year. Okay. So what lies beyond 1 year?
Yes, okay.
Yeah. So within 1 year, if you just look at planets, within an orbital period within less than 1 year, there are very few gas giants, Jupiter-like planets, massive planets around M-type stars or polar stars. That's all I'm saying. So this is sort of a statistical result, and it doesn't mean that you don't have any Jupiter around M-type. But then there are many more smaller planets around M-type stars than Jupiters, and there are many more Jupiters around G-type sun-like stars than M-type star. Yeah, so the metallicity. So metallicity is just the heavy element content of the star. And what we astronomers call metals, anything other than hydrogen and helium, we call metals. But it's what here in the rest of the talk, what we'll be using iron to measure as a measure of metallicity, the iron content of the star. And this is because it's much easier to calculate the iron content of the star, because iron has several lines, absorption lines in the optical wavelengths, and historically that has been used widely. So yeah, so Ravi has posted something. No, I don't have to do that. No? Yeah, so that's for the audience. Okay. Yeah. So interestingly, the planet properties seem to very strongly correlated with the metal content of the host star. Let us see how they are related. So this was realized very early. Even see the first planet around the Sun-like star was discovered in 1995. And by 97, 98, this correlation had emerged, and then there were mostly planets discovered by radial velocity Doppler shift method, and it was very clear that Jupiter-like planets were preferentially found around metal-rich stars, which have solar or supersolar metallicity, and not subsolar metallicity. That's what we mean by that. And then the latest studies have consolidated this result. This is one of the most robust observational results in the entire exoplanet observational studies, that Jupiter-like gas giants are preferentially found around metal-rich stars, where the Fe by H value, the iron content, is higher. So here is one representation of that. I have shown 3 histograms, distribution of the empty histograms are stars which do not host planets. I mean, that's a little problematic, but the beige color is histogram is stars hosting small planets, and the blue is stars hosting giant planets. And you can see the iron content of the metallicity progressively of the host star, on average, progressively increases, going from planets which do not host any planets, stars which do not host any planets, to stars which host small planets, which are defined as having radius less than 4 Earth radius, smaller than Neptune. And when you go to giant planets hosting stars, they typically show much higher metallicity. And this has come out in various forms. I think several groups have independently shown this. Here is one such representation that is done by my student Mike Merrick. Yeah, I think so. Basically, this is an occurrence rate diagram. So this is after taking care of all the selection effects. So here the different colors are the red histogram. Red color is for subsolar metallicity or iron content less than that of the sun. Green, solar metallicity, and blue supersolar metallicity or iron content greater than that of the sun. What you notice is when you go to giant planets, the larger and massive planets, they are preferentially found around host stars which have supersolar metallicity. And when you go to smaller planets, it doesn't really matter. There's no clear trend. But clearly, giant planets require high metallicity stars, it looks like. Not just that, and one of the interesting things that we found was, so this if you were to plot average metallicity, averaged in bins as a function of the planet mass, going from Earth-like planets to about Saturn, Jupiter here. So 300 Earth mass is Jupiter mass, Jupiter is somewhere here. So it gradually increases average metallicity. This is an average metallicity, remember, and in a given bin, it increases. It increases systematically when you go to Jupiter size, and then it sort of dramatically turns around, and it doesn't increase anymore when you go to planets more massive than Jupiter's. So this was something very interesting that we were one of the first people to point this out. So super Jupiters do not appear to, the planets more massive than Jupiters do not appear to prefer metal-rich stars. So they are found in all kinds of stars. So this, others also have pointed out the same result. Statistically, that trend is seen. So why do we see this? So I've tried to sort of summarize some of the things that we have seen so far. So cool stars do not appear to host giant planets. So this is one possible answer could be that if you see, the planets are thought to be formed in the protoplanetary disk. When the stars form from the collapse of a molecular cloud, and it forms a disk around it, and we believe that its planetary systems are formed out of this disk, which we call the protoplanetary disk. So there have been a lot of studies in the last 2 decades or so on measuring protoplanetary disk masses, and what we see is that the disk mass around different spectral types has a tendency that you see more and more massive disks around the hotter stars. When it comes to cooler stars, the disk mass is low. So disk mass scales with stellar mass. So probably this in a less massive disk, it's difficult to form Jupiters. We don't. This is not an well-answered question yet. And a second trend that we are seeing was Jupiters are preferentially found around metal-rich stars. So the way we understand this is according to the modern star formation theory, both the star and the protoplanetary disk and the planet that are formed out of protoplanets, they all form from the same material, same molecular cloud material, which has a given metallicity. And it it has got to do with the formation of Jupiters in the standard canonical classic planet formation theory. Jupiters are formed via what is known as a core accretion model or scenario, where in the protoplanet, the small dust grains stick together, coagulate, and grow, and they grow into larger meter-sized bodies, and then they become planetesimal. Then the planetesimals, kind of combine to form larger bodies up to. When you form a kind of a 10 to 15 Earth mass core, you can accrete gas from the disk and form a Jupiter-like planet. This is what core accretion formation scenario of Jupiter tells us. So in such a scenario, to form this 10 to 15 Earth mass core faster and more efficiently, if that can happen in metal-rich disk. Simulations have shown that the disks are metal rich, you can form this 10-15 Earth mass rocky core, iron core, faster, and that will kind of accelerate the Jupiter formation. And that is perhaps what's reflected in this correlation that we find that the Jupiters are preferentially found around metal-rich stars. There is a question on the chat window. Do every giant planets form by our core accretion process? Yeah, Jupiter-like planets, that is what we believe. Jupiter-like planets form core accretion thing. So in a minute, I'll come to the other one. So if the core accretion formation channel is what is causing this trend that we see, that the Jupiter gas giants are found around metal-rich stars, then as I have shown you in the last slide, super Jupiters, planets more massive than Jupiters, do not show this. So what does it mean? So in one of the explanations suggested is that probably super Jupiters do not form via core accretion. They don't form by forming first a 10 or 20 Earth mass core and then accreting gas, but rather they form via gravitational fragmentation of the disk itself. This can become gravitationally unstable if it is sufficiently massive. So maybe they form via the gravitational collapse, local collapse, or gravitational collapse of the disk itself. So then it doesn't depend on metallicity. You don't need to form a core; it's just a gravitational collapse. These are just suggestions, and this is an open problem. So how much time do I have? One other issue that we can look at is which depends on metallicity, again in the same sense that I was describing, is the formation of giant planets itself. But initially, the first planet that we had discovered, a giant Jupiter-like planet and very close to the star. So these are so close to the star that, if you work out the equilibrium temperature, that will be, in excess of 1,000 or sometimes even, 2,000 Kelvin. So these are really hot Jupiters. So such class of objects, were generally called as hot Jupiters. So and they are very close to the central star. The problem is in core accretion, it's not very efficient, very close. So this is the innermost edge of the protoplanetary. There isn't enough material there to form. So it was always a mystery. How do you form this? There are currently two possible explanations. I mean, the mechanisms that put forward. One is somehow in situ formation in the if the disk is extremely metal rich or something, or the second mechanism, which is probably more likely, is that Jupiters form like the where we are Jupiters form, maybe 3-4 AU astronomical units, because it's much easier to for the grain growth and formation of this the rocky core is much easier beyond what is called the snow line. See, snow line is, for a given species, snow line is a radius in the disk, protoplanetary disk, beyond which that species condenses into ice. And inside the snow line, that species is in the vapor form, right? So we are outside of the snow line. The dust grains can have ices, water ice or CO2, whatever, depending on where the snow line is. And then that significantly increases the sticking probability, and then they can grow much faster. So Jupiters most likely are formed outside the snow line, and then somehow they migrate inwards. So so high eccentricity migration can cause this. So this is something that we wanted to look at. So after looking for the correlation between metallicity and the planet mass, the next thing that we want to do is how do Jupiters correlate with the stellar metallicity? Jupiters at different orbital periods, So here what I've shown is the first bin is hot Jupiters. Jupiters with orbital period less than 10 days. That's very close to central star. The second middle bin, as is shown here, we call it the warm Jupiters, between 10 days and 365 days, And the last bin is the classical Jupiters, where our solar system kind of Jupiters beyond 1 AU, orbital period, greater than 1 year. So what is really interesting is, and if you also show them, divide them into their eccentricities, whether they're circular or highly eccentric, high eccentricity sources in this bin show higher metallicity, and low eccentricity ones show slightly lower metallicity. So the idea, I don't want to spend too much time on this. It's slightly complex concept, but the idea is that if you have some more high eccentricity Jupiters, then they can migrate inwards, and then once they're close to the central star, they can tidally circularize, and that's one formation pathway for hot Jupiters. And if the disk is of higher metallicity, then that can aid and accelerate this process, and that is probably what we are seeing here. But I don't want to spend too much time on this. Yeah, so I can go on for another 10-15 minutes, maybe. Okay, I see a hand here. Varun, you want to ask a question?
Yes, sir. Can you go back to the previous third last slide? The one with, yes, this one. Sir, is it possible that because you said that Jupiter-sized planets do not appear to prefer metal-rich host stars. Is it possible that
Jupiters are preferentially found around metal-rich stars?
No, sorry, super Jupiters.
They don't. Yeah, they don't show.
So,
yes.
Is it possible that it is? We should frame it like super Jupiters do not appear to prefer metal-rich host stars because of our detection. Just the detection is such that, because you only told that there are some planets The first assumption is that these all graphs are for the planets which have orbital period less than 1 year. And secondly, it is very easy to detect the planets which are Jupiter sized and which are close to the star. So is it possible that
these are all these super Jupiters are also within 1 year, what I have shown earlier.
Yes,
so all
yes.
this that I'm talking about. So orbital distance is okay, and they are more massive than Jupiter, so they are more easy to detect. So that is not an issue. Detection may not be an issue here.
Yeah. So rather than saying that this is the distribution, can you go back to the previous slide, to the one before this? When the one which had bar graphs. Yes, this one. So rather than saying that there are numerous Jupiters for the range 8 to 20 radius for the blue color is more because the detection is more in the blue color, and not that there are actually
No,
the
Varun,
red ones
see,
are less.
this is occurrence rate. Here those effects have been corrected for. So this is kind of a true representation. We have also taken out the radius dependence here. See, I'm not really going into the
Okay,
technical
okay,
details
okay,
here. So this is
okay,
okay. This is there's no observational bias here. And the super Jupiter
Mhm.
thing, it's not just us who are saying this. So subsequent studies have confirmed this more or less.
Okay.
So super Jupiters does not seem to show that as strongly as Jupiters. So, yeah.
Okay.
And then this is a statistical statement. It doesn't mean that you don't find Jupiters around a metal poor star, but on average, you see certain trends.
Yeah, the point was that we might miss out on Earth-sized planets because of our detection techniques, and not because there are actually less number of Earth-sized planets.
Yeah, I'm not talking about Earth-sized planets. I mean, we're just talking about the Jupiter formation right now. Yeah. Okay. Yeah. Any other questions? Yeah, there is one on chat. Is there any difference between brown dwarfs and super Jupiters based on? Yeah, we don't know yet. That's a good question. See, it's at a continuum. See, brown dwarfs are, maybe you guys heard about this. So brown dwarfs are sort of failed stars who just fail to ignite hydrogen in their cores, right? So that mass range is less than 80 Jupiter mass, anything above 80 Jupiter mass, any object above 80 Jupiter mass or 0.08 solar masses can actually have hydrogen fusion in their core, and they shine like a star. Anything less than that are brown dwarfs. 80 Jupiter mass is brown dwarf, but brown dwarfs cannot burn hydrogen in their core, but they can burn a little bit of deuterium. So to burn deuterium, the temperature needs to be at least a Kelvin or slightly more than a Kelvin. So up to 80 Jupiter mass to 13 Jupiter mass, that's a brown dwarf regime. The structure is very different. They're burning slightly deuterium, but below 13 Jupiter mass, you can't even burn deuterium. The central temperatures never reach there. These dividing lines are rough ones. I mean, not very, don't take it too seriously, but roughly about that. So, yeah. So Jupiter's, So anything above 4 Jupiter mass and less than 13 Jupiter mass is what we call super Jupiters. These are so it's probably a continuum. So we don't know exactly how they form. Yeah, brown dwarfs, at least we know that they form like stars in the sense the collapse of the gravitational cloud, and then they also, brown dwarfs also have disk around them. But then now we know from high sensitivity, high resolution, angular resolution images that even planets that are forming in their disk, protoplanet disk, they can also have, planetary disks, circumplanetary disks. So it's all probably a continuum. We can't know it's so there are. So we are learning, when we learn more and more, there are similarities but differences as well between these various formation scenarios. All right. So yeah, maybe do I want to? I think I'll skip this. This is a lot of stuff. So maybe I'll just summarize what we have discussed so far, and then after that I'll talk a little bit about star-planet interaction, and then stop there. So what have we learned so far from demographic studies? From mostly that planetary systems are quite common, and the total occurrence rate is about 1.3 planets per star, implying that there are more planets in our galaxy than stars. And most of the planets are likely to be small planets, the super Earth, mini Neptunes, and Earth-like planets, than gas giants. And then we also learned that there are more planets around cooler M-type stars than Sun-like stars, but most of them are smaller rocky planets. And then we also saw that the solar system is not an archetypal planetary system, but we should bear in mind that all these results are strictly true for compact systems, planetary system with orbital period less than 1 year or so. But there are systems, there are a good number of systems which are very compact, very unlike our solar system. And the third thing that we have learned is that planet properties, the observed properties such as radius, mass, and orbital period are strongly dependent on the host star properties. It's as we saw that larger and more massive planets are preferentially found around metal-rich stars, the Jupiter-like planets. Cooler stars have fewer giant planets but host many more smaller planets than Sun-like stars. And this has implications for planet formation theories. And I haven't gone into the details because this is still it's a very fluid area. I mean, these are not settled issues. So we are seeing these observed patterns, and then here is one example, one area where theory lags observations. So one of the questions, as I was saying, is that comes out of this demographic studies, particularly with this correlation that we find, that the planet properties show a very strong dependence or very strongly correlate with the host star properties. Is that so why is that? I mean, do planetary systems preserve their memory of their birth? So this is something that's strongly debated in literature. Otherwise, why should you have such a correlation? As I said, it has important implications for planet formation theories. I can just stop here for a minute and take a couple of questions before I quickly go into talk about a couple of things on the star-planet interaction that might be of some interest here. If there are any questions, I can wait for a couple of minutes. Yeah, then we can take questions towards the end. Let me go on to see one of the we saw the most of the systems that we had discovered because of the selection effect and the particular detection techniques, sensitivity, etc. They are compact systems, unlike our solar system, and most of them are within 1 year, or some of them are extremely compact, right? And this has and I talked about hot Jupiters, and which is very close to central star, and the several planets are very close to central star, and this has important consequences for their evolution, because the stellar radiation can wreak havoc in their atmosphere, and their subsequent evolution. So one such thing that that has come out of the demographic studies is what is known as the radius gap, or the Fulton gap, named after Fulton, who first pointed that out. So the radius gap is simply, if you were to plot a distribution of planet sizes or the radius, you see a apparent gap between super Earths and sub-Neptunes, between 1.7 Earth radius and 2 Earth radius. There seems to be a dearth of planets in this radius range. If you actually plot it in a two-dimensional plane with planet size or the planet radii on the y-axis and orbital period on the abscissa, and what you there is a question about what about the gap at 0.9 Earth radius. So we are not complete there. So this has to come out in occurrence rate studies. So less than 1 Earth radius, we are not complete, so that we cannot even correct for it. So we cannot say anything at the moment. So now if you have it in a plane, a planet size and orbital period, it actually has a dependence on orbital period also, this radius gap. So what is plotted here is the density, the number density of planets in the color scale. Yellow, white is lowest density. You can see this density, right? So the gap. So that gap has a orbital period dependence also, and this is generally called the radius valley. So dividing the super Earths from sub-Neptunes. So what is the origin of this radius valley? Why does this gap exist? So people have there have been a few suggestions. One of them was that somehow these planets are when they form they are like this, and these planets are losing their atmosphere somehow, and then become like this. And some of them they're sufficiently massive they're able to hold on to the atmosphere, and then that is how the divide happened. So why do they lose their atmosphere? So there are two mechanisms that people talk about predominantly. One is the photo operation, the XUV photons, the UV X-ray photons from the central star. It can evaporate off the atmosphere. So, and the other source, the driving source that people talk about is core-powered mass loss. The planet, the inner core of the planet itself, radioactively decaying, and that heat can also evaporate off. It's not easy to distinguish between which is this, but what we can really show is that photo operation, the central star does have an effect, and this is something one of my students that looked at. He tried to model this, and then I'm showing a video here. First, look at the left panel. Now when it starts, you see the gap forms, and the gap actually moves in time. The valley, the radius valley, when you run with the photo operation, all that, it actually is a function of time. The valley keeps moving up. There's been to larger and larger radius. And so if the planetary systems that you're talking about are very young, a giga-year or less old, then the radius valley is the radius gap would be slightly to the left, to the smaller radius. And as time progresses, so the planetary system that we look at now, they are typically of 3 to 5 giga-years old. They're mature planetary systems. So then the gap is at 1.7 to 2 Earth radii. But what really came out of the simulation is that also the mass radius relation is also changing. Initially planets are very fluffy, and quickly they lose atmosphere or contract, and eventually kind of match with this. This orange line is what is called the Chen-Kipping mass radius relation derived from the observed mass radius of the planets. So it settles down to that, but that is also has a time dependence. So the planets evolve strongly, especially in the presence of the radiation from the central star. There is one other thing that my group has been interested in, to detect the signatures of star-planet interaction via radio emission. So the idea is that exoplanets can also have magnetic fields, and the radio emission from them is the only way to detect them, and to measure the magnetic field strength. And magnetic fields are important because they provide us important clues for the internal structure of the planets also. So the mechanism, I don't want to go into the details. The mechanism, there are a couple of different mechanisms, but for radio emission from exoplanets. But both these mechanisms predict the peak emission. Radio emission is likely to fall within several tens to few hundred megahertz, and this is the wavelength range or frequency range where our GMRT, the giant meter wave radio telescope in Pune, operates. And my student and I have been looking for signatures of radio emission from exoplanets. See, lot of people have been. This is a very interesting topic, and different groups have been looking for this, and unambiguous detection has not been reported yet. There have been a couple of claims, but it's still debated whether it's really the radio emission from the star planet. So we carried out an extensive survey with GMRT, about 300 hours, and then we observed 3 different kinds of sources. I can discuss this more during the question and answer session. Just want to show that. So we have not been able to detect, but we were able to place some of the strongest upper limits for detection, and from which we were able to constrain some of the mechanisms and roll out some of the theoretical mechanisms predicted. So for different mechanisms predict certain expected flux, and once you see that you don't see that kind of flux, you can roll out certain mechanisms, and yeah, so we just wanted to put out there. And we recently had a detection from a star called AU-Weak. It's a young star, but we will I'll talk about it later. So what I'll do is I'll stop here, and then maybe we can I can take questions and discuss the rest of it in the next 15 minutes. I take questions. Yeah, any questions? Oh, I see one hand. Sakshi Gupta. Yeah, Sakshi, please go ahead and ask the question. Sorry, I can't. Can you others hear Sakshi? I can't hear Sakshi at all.
No, we can't hear Sakshi. Sakshi, you can type your question in the chat box. If audio is.
Hello.
Yes, now we can hear you.
Yeah.
Okay. So yeah, hi. So I also work on star planet interaction at CESI. So I was curious to know, if time permits, can you give a bit detail? How do we theoretically predict what will be the radio emission? I mean, I know it's difficult to do observation, but how do we predict?
Yeah, so it's quite widely done in literature. So this this mechanism is called as ECMI, right? Electron cyclotron maser interaction. So it's sort of a broad emission, continuum emission, but it kind of peaks at the cyclotron frequency. And if you so of course it depends on the magnetic field, what's the strength of the, so it depends on which mechanism. There are 2 mechanisms, like one is the star planet interaction, where the stellar wind provides electrons to the planet's magnetic fields to accelerate and cause ECMI. In that case, if you know the stellar magnetic field, you can roughly predict the peak thing. But as you can see, from these predictions, when you go and observe, you don't see, detect anything. So clearly, there are some issues with the models. One other mechanism is something similar to what we see in our solar system, the Jupiter Io mechanism, Jupiter's moon Io. So there it's a planet's magnetic field that comes into effect. So then the problem is we don't have a priori knowledge of that. But from certain models, for example, there have been some recent models about planetary magnetic fields. One can use that and predict. So you're right. I mean, a theoretical prediction, it's not on a very solid footing. But once one has to have some estimates of what one is looking for. Yeah, but so many of these, if you look at the last decade or so, many of these predictions, they all had Millijansky kind of fluxes, predicted. We don't see that. GMRT is very sensitive. We can reach to RMS of a few tenths of microjanskys at 650 micron, for example, 650 megahertz band, the band 4. So there we can also, at 650 megahertz, we can also observe polarization. GMRT has polarization capability, so one can also see that as well.
Thank you.
Any more questions?
Hey, Professor, I just had one more question. Is there any relation between a host star and a TTV? Like, is there something?
Host star and what?
And a TTV, like a transit timing variation planet, like with a planet with a declining orbit.
And relation with host star.
Yeah, like, is there something noticeable about TTVs?
I don't know. I don't. Yeah, not. I not that I know, but yeah. So you're saying
Thank you.
TTV planets detected using uh, TTVs, the transit time variations. Some are found around some particular host star or something. Not that I
Yeah.
know.
Okay.
Yeah.
Because
I
I just wondered.
I
Because,
don't know if there is any such. Yeah. Yeah.
uh, because I just wondered, like, since they have a declining orbit, maybe they're prone to a few a certain kind of stars, and like for their behavior and such.
So, Manoj, may I just chime in
Yeah.
here?
Yeah.
For a
Please, Ravi. Yeah.
Yeah. So, Harshita, the TTVs are for planet interactions, right? As you know, they can be observed around any kind of star, irrespective of the stellar type. If the star has a multi-planet system. So, are you saying are TTVs observed around a particular kind of star? Is that the question?
Yeah, I just wondered if they are prone to certain stars, or if they have any statistical significance.
If your question is, are multi-planet systems found or around a particular kind of star, I think Manoj mentioned about the metallicity relation of planet occurrence and disk mass, right? So that then there could be potential multiple planets, and then if there are, then if it is transiting system, then there could be TTVs around it. So there is not a clear, there is no relation between stars and the TTVs observed, just because TTVs are only for planets.
Yeah. So do you mean that TTVs are always found in multi-planet systems, and so they cannot be the only planet in the system? Like, is that a takeaway?
Yes, right. So as Manoj pointed out again, you need a transit timing variation, right? So the reason why there is a timing variation in a transit is because some other planet is disturbing it.
Okay.
So you need multi-planet system. Yeah.
Okay. Thank you, Professor.
Yeah.
I just have a follow-up question. So you have shown two methods. One is Fulton radius gap, and another is radio emission to detect to get the signatures of star-planet interaction.
No, not really. I mean, I was just showing Fulton gap as star planet interaction is both ways, no? And stars affecting the planetary evolution and planet affecting the sun. So I was just showing and putting it there. So Fulton gap is not really something that people do for star planet interaction, but that's I was just talking about that as an evidence of how star and planet they are close close by. Radio emission I chose to show. We radio emission is one of the things. Other things is other thing that we also had looked at is UV. If you look at the stellar flux in UV, and look for some variation or something.
Lyman
So people have done that. Yeah.
Okay.
Yeah. Was that your question?
Yeah. So that is what I was asking. So I've since last few years I've seen few papers of Lyman alpha detection as a proof for star-planet interaction. So is it also very challenging from observational point of view, or is it
Lyman alpha is very challenging because you have to first of all go up to observe it. I mean, in Leo, the low Earth orbit, it's like the Earth also has, there are geocoronal lines also, but people have done it from the satellites, I think so. But Lyman alpha is one thing, but that's you could call it star-planet interaction. That's kind of evaporating flow. People have interpreted as or arising out of evaporating flows. But there have also been other studies looking at UV, maybe the calcium, magnesium, calcium HNK lines or resonance lines, and see the variation in this if it is correlated with or modulated by the planet's orbital period and things like that. So this is, I think, so that some groups have done these studies. We also looked at the UV flux from Galax. We did the major survey, but that we were looking at the continuum thing. So it's our conclusion was we can't say very much from the continuum UV. So it has to be some, the resonance lines, the chromospheric activity lines. Lines that trace chromospheric activity and then modulated by the planetary orbital period. Because stars also, late type stars also are very active chromospherically, even without a star. So it's a distinguishing between star-planet interaction and the stellar chromospheric activity is hard.
Okay.
Any other question? Questions, comments?
Hello, participants, you can unmute yourselves and ask, or you can put it in the chat box. So we have a comment that the session was good, and thank you for your very informative session.
Manoj, can
Okay,
I ask?
thank you, Dr. Sham. Yes, Dr. Ravi.
No, I was just asking Manoj that if students or anyone want to have more information about the material.
Yeah, I'll be happy to, they can write to me, and I will, as Prachi was saying, I'll, in a couple of days, I'll share this slide with you, and whenever you, want to, if you want to keep it in the central repository, I'll be happy to share. I can send it to you.
Thank you.
That's what you were asking, Ravi, right?
Yes, and any background material, reading material, if they.
Yeah. So I can leave my email address with you or Prachi, and they can make it available to the students. They can write to me, and I can share material or point them to
Okay.
references, etc.
Yes.
Sure. Thank you.
So we have a WhatsApp group. On that, maybe I will share your email ID, or you can also put it in the chat box here.
But chat box, that may not be people. I can send it to you. You can share.
Sure. Okay. Yeah.
Yeah.
Okay. Yes. So people are asking about email IDs. So yes, we will be sharing Dr. Manoj's email ID on the WhatsApp.
Yeah, I can share it. I'm typing it in the chat window. If those who want to copy, they can copy here. But I can also pass it on. You have my ID. You can share.
Yeah.
I'm happy to. Happy to oblige. I'm happy to provide references.
I have also pasted it on the WhatsApp group.
Sure.
For people. Okay. So yes, thank you so much, Dr. Manoj. It was a very nice, informative talk, and good interactions we had during the session. So on behalf of Pune Knowledge Cluster, I thank you for accepting our invitation and joining today for this session. Thanks.
Thank you. Thank you.
Dr. Ravi, would you like to say something? Yeah.
Oh, I just want to say real pleasure to have you here, Manoj, and thank you so much for taking the time.
Thanks, Ravi. Thanks for having me, and thanks for organizing all this. I think we owe it to you to the driving force behind this whole initiative, not just this, and all those things that.
Right.
Thank you, Prachi.
Dr. Ravi. Thank you so much.
I hope at least some of the students might get interested in exoplanets, and we need to really grow the group in the country, the community in the country. Yeah,
that sounds good. Yes, that's for sure. Thank you.
Yes. All right. I'll stop sharing, I think. Yeah. All right. So bye everyone, and I'll talk to you all sometime soon. Yeah. Have a good evening.
Thanks. I'll end the meeting.
Yeah.
Okay.
Thank you.
Thank you. Bye.